Just over 400 million miles from Earth, in the final days of 2025, an interstellar visitor that had already stunned astronomers with its speed and its size was doing something none of the previous two interstellar objects ever detected had done for long enough to matter, venting a bright, gas-rich cloud into space, freshly warmed by its closest pass by the sun, in exactly the kind of state a spectrograph needs to read the deepest chemical secrets locked inside its ice. Astronomers had one narrow window to point the most powerful telescope ever built directly at it before that glow faded and the comet slipped back into the dark for good. They took it. And on June 22nd, 2026, the results of that observation were published in the journal Nature, revealing something that, in the plain words of NASA's own science communications team, surprised the researchers who found it. This comet is old, not old in the way a rock from the early solar system is old. Old enough that it may have started forming before our own sun, before Earth, before almost every star currently visible in the night sky, somewhere between 10 and 12 billion years ago, during a period of the universe's history astronomers call cosmic noon, when galaxies across the cosmos were forming stars at the fastest rate they ever would. This is the story of what the James Webb Space Telescope actually found when it turned its instruments toward Comet 3I Atlas, as the object began its long journey back out of our solar system, and why the chemistry hidden inside that faint, fading glow of gas is now reshaping how scientists think about just how unusual, or how ordinary, our own solar system might actually be. To understand why this particular discovery carries so much weight, you first need to understand exactly what 3I Atlas is, how astronomers came to study it at all, and why interstellar objects like it are so rare and so difficult to observe in the first place. 3I Atlas is the third confirmed interstellar object ever detected passing through our solar system, following 1I Oumuamua in 2017 and 2I Borisov in 2019. It was first spotted on July 1st, 2025 by a survey telescope in Rio Hurtado, Chile, part of a NASA-funded early warning network called ATLAS, originally built to identify asteroids that might pose a risk to Earth. The object's motion immediately marked it as something unusual. Nearly everything in our solar system, every planet, asteroid, and comet, is gravitationally bound to the Sun, following a closed elliptical orbit that loops around again and again, sometimes over the course of thousands of years, but always eventually returning. 3I Atlas wasn't doing that. Its path was hyperbolic, moving too fast, on too straight a trajectory for the sun's gravity to ever capture it into a stable orbit. When astronomers traced its route backward, they confirmed what the trajectory had already suggested. This object came from interstellar space, borrowed a portion of our sun's gravity to bend its course slightly, and was already on its way back out, never to return. By the time it was discovered, 3I Atlas was still roughly 410 million miles from the sun, out near the orbit of Jupiter, and moving at a speed that would eventually peak at around 153,000 miles per hour at its closest approach to the sun, the fastest velocity ever recorded for any object passing through our solar system. That speed alone made it clear from the outset that no spacecraft launched from Earth could ever hope to catch up to it. Whatever this object had to tell us, it could only be learned by watching from a distance, using the most sensitive instruments currently available, during the brief window it spent close enough to the sun to become active and observable at all. Over the following months, that's exactly what happened. Multiple observatories, including the Hubble Space Telescope, ground-based facilities across several continents, and orbiting X-ray observatories, turned their attention toward 3I Atlas as it swung through the inner solar system, making its closest approach to the sun on October 30th, 2025, at a distance of about 130 million miles just inside the orbit of Mars. Those earlier observations revealed a great deal. The comet's teardrop-shaped coma, a rough estimate of its solid nucleus somewhere between roughly 1,400 feet and 3.5 miles across, and early detections of gases including carbon dioxide, water vapor, carbon monoxide, and a sulfur-bearing compound called carbonyl sulfide, along with, in later, more detailed observations, methane. Each of those findings added a piece to the puzzle. None of them, on their own, could answer the deeper question scientists really wanted to answer. Where did this object actually come from, and how old is it? Answering that question required something more specific than simply detecting which gases were present. It required measuring the precise isotopic ratios within those gases, the relative proportions of slightly different, slightly heavier or lighter versions of the same basic elements, ratios that function almost like a chemical fingerprint, one that can reveal not just what a comet is made of, but the specific physical conditions, the temperature, the density, the age of the environment it originally formed in billions of years ago around a star we will likely never identify. That kind of precise isotopic measurement requires an extraordinarily sensitive instrument and an object bright enough and active enough to provide a strong enough signal to measure accurately. as 3I Atlas moved away from the Sun in December of 2025. Still freshly warmed from its close solar passage, its icy surface was actively venting a rich, bright coma of gas, providing exactly the kind of strong, chemically detailed signal astronomers needed. A team led by Martin Cordner used the James Webb Space Telescope's near-infrared spectrograph, commonly abbreviated as NIR-SPEC, one of Webb's primary science instruments, to capture detailed measurements of that outgassing coma during this narrow, favorable window before the comet faded too far to study in this kind of depth. What NIR-SPEC detected, and what the resulting analysis revealed once fully processed, is the heart of this entire story. Webb's instrument detected a specific molecule called HDO, a variant of ordinary water in which one of its two hydrogen atoms has been replaced by deuterium, a heavier isotope of hydrogen that contains an extra neutron in its nucleus, sometimes referred to informally as heavy hydrogen. By carefully comparing the amount of this heavy water, HDO, against the amount of ordinary water, H2O, present in the comet's coma, Cordner's team measured what's called a deuterium to hydrogen ratio, arriving at a precise figure of 0, 98%, with a small margin of error of about 0.06%. That number, on its own, might not sound especially dramatic. Its significance becomes clear only once you compare it against what astronomers already know from studying comets that actually belong to our own solar system. According to the published findings, this deuterium to hydrogen ratio measured in 3I Atlas is roughly 34 times higher than the average ratio measured in comets native to our solar system, and nearly 10 times greater than the average value typically observed in protostars, the young, still-forming stars, where much of a solar system's earliest ice is believed to originate. Within our entire solar system, only one place has ever shown a comparably high ratio, the atmosphere of Venus, and only because Venus's atmosphere underwent an extraordinarily long, unusual evolutionary history, entirely different from how a comet's ice forms and remains preserved. Here's why that specific ratio matters so much to scientists trying to reconstruct where and when an object formed. Deuterium enrichment in water ice isn't random. It's a direct physical consequence of the temperature at which that ice originally formed. Colder formation environments naturally allow for higher deuterium enrichment because the specific chemical reactions responsible for incorporating deuterium into water molecules become more efficient and less easily reversed at extremely low temperatures. Based on the enrichment level measured in 3I Atlas, researchers concluded that much of the comet's ice must have formed at temperatures below 30 degrees above absolute zero on the Kelvin scale, equivalent to roughly minus 400 degrees Fahrenheit. An extraordinarily cold environment even by the standards of interstellar ice formation. That measurement alone would have been a significant finding on its own, but Cordner's team didn't stop with deuterium. Webb's data also revealed detailed information about the ratio of two different isotopes of carbon present in the comet's coma: ordinary carbon-12, the most common form of carbon found throughout the universe, and the heavier, rarer isotope carbon-13. Much like deuterium enrichment in water, the relative proportion of carbon-13 in an object's ice can serve as a kind of chemical clock, since carbon-13 enrichment is known to gradually increase within stellar systems over long periods of time as those systems age and evolve. According to reporting on the published findings, the level of carbon-13 enrichment detected in 3I Atlas was interpreted by the research team as evidence pointing toward an extreme age for the comet, potentially stretching back as far as an astonishing 12 billion years. Put both of those findings together, the extreme deuterium enrichment pointing to an extraordinarily cold formation environment, and the carbon isotope ratio pointing to an extraordinarily old age, and you arrive at the picture NASA's own science communications team described directly in their published summary of the research. The data on the composition of 3I Atlas imply that it might have originated in a very cold stellar system from much earlier in the history of our own galaxy, potentially forming as long ago as 10 to 12 billion years. During the period of the universe's history astronomers refer to as cosmic noon, when star formation across the broader universe was occurring at its highest rate ever recorded. It's worth taking a moment to actually sit with what that time frame means, because it's easy to read past a number like 12 billion years without fully grasping its scale. Our own sun and solar system formed roughly 4.5 billion years ago. 12 billion years ago, more than 7 billion years before our own sun ever ignited, the broader universe itself was still in a comparatively early, chaotic, rapidly evolving phase of its development. If 3I Atlas truly formed that long ago, it means this small, icy object, now passing quietly through our solar system on its way back out into interstellar space, has been drifting through the galaxy, largely untouched, for a length of time roughly 2.5 times longer than our own solar system has existed at all. Whatever star system it originally formed around has very likely long since changed beyond recognition, potentially having already run through its own stellar life cycle entirely, its original star possibly having already died exploded, or faded away into a stellar remnant sometime in the vast stretch of time since this particular piece of ice first formed within its planetary disk. NASA's research team offered a specific physical scenario to help explain how an object this old might have ended up loose in interstellar space in the first place, rather than remaining bound to whatever system it originally formed within. According to their published analysis, it's possible that the system 3I Atlas originated and existed within a relatively cold, dense cloud of gas and dust, and that the comet itself was gradually ejected from that system as the surrounding environment aged and warmed over time, a slow, gravitational process capable of flinging icy bodies out of their home systems entirely, sending them drifting through the emptiness between stars for billions of years afterward, until, by pure chance, one of them happens to pass close enough to another star, in this case, our own sun, for its ice to be warmed again and briefly reveal, through the faint glow of its outgassing coma, the chemical fingerprint of the ancient, long-vanished environment it first formed within. Stephanie Milam, a researcher at NASA's Goddard Space Flight Center and a co-author of the study alongside Cordner, offered a comment that captures precisely why findings like this matter to scientists beyond simple curiosity about a single object's age. Speaking about the discovery of these rare isotopic ratios, Milam noted that finding them is fascinating on its own, but that the bigger picture involves examining the broader possibilities of prebiotic chemistry occurring elsewhere across the galaxy. As she put it directly, so far, we know of only one place in the vast cosmos where the right chemical ingredients actually came together to produce life: our own solar system, our own Earth. Studying the detailed chemistry preserved inside an object like 3I Atlas, formed under conditions and during a period of galactic history entirely different from our own solar system's formation, offers scientists a genuine, if narrow and fleeting, opportunity to compare the chemical raw materials available in a completely different corner of the galaxy's deep past against the specific combination of ingredients that, in our own solar system's case, eventually gave rise to life. Cordner himself offered a similarly reflective comment on the significance of the observation, one that captures the genuine, grounded excitement scientists felt about this particular opportunity, without needing any exaggeration to convey it. He described the observation as a unique opportunity to study an ancient object from the distant galaxy, one that likely predates our own sun and solar system entirely, a rare chance to examine physical material that formed under conditions scientists can otherwise only study indirectly through theoretical modeling and observations of extremely distant, extremely faint galaxies, rather than through any physical sample close enough to actually measure directly. Webb's findings didn't stand entirely alone. A separate complementary study, conducted using the European Southern Observatory's very large telescope in Chile and led by astronomer Cyrielle Opetom of the University of Edinburgh, examined a different piece of the comet's chemical puzzle. The ratios of carbon and nitrogen isotopes present specifically within a compound called cyanide, another molecule detected within the comet's outgassing coma. That independent study, using an entirely different telescope and an entirely different set of chemical measurements, reinforced the broader picture emerging from Webb's own observations, adding further, independently gathered evidence supporting the conclusion that 3I Atlas carries chemical signatures distinct from and considerably older than anything typically found in comets native to our own solar system. Having two separate research teams, using two different world-class telescopes and two different chemical tracers, arrive at broadly consistent conclusions about the comet's ancient, unusual origins, adds real, meaningful scientific weight to the overall finding, the kind of independent cross-verification that genuinely strengthens confidence in a result like this one, rather than relying on any single measurement or research group alone. It's worth being direct about one detail that's occasionally distorted in less careful retellings of this story. 3I, Atlas's unusual size, speed, and chemical composition did, understandably, generate some public speculation, including brief suggestions, floated by a small number of commentators, that an object this unusual might not be a natural comet at all. The overwhelming body of evidence gathered by NASA, the European Space Agency, and the broader international astronomical community firmly supports the conclusion that 3I Atlas is exactly what these newest findings describe: an extraordinarily old, but entirely natural, interstellar comet behaving in every observed respect the way ordinary cometary ice behaves when warmed by a star, just carrying chemical fingerprints considerably older and colder than anything previously measured in an object passing through our solar system. The Webb and Very Large Telescope findings described here don't just fail to support more speculative explanations, they actively strengthen the case for a natural origin by providing detailed, physically consistent chemical evidence that fits precisely within well-understood models of how comets form and evolve within any sufficiently cold, ancient stellar environment, wherever in the galaxy that environment happened to exist. There's a broader scientific theme running through this entire discovery that connects it directly back to the two interstellar objects that came before it, Oumuamua and Borisov, and it's worth drawing that connection out explicitly. Each of the three confirmed interstellar objects detected so far has told scientists something meaningfully different about the range of conditions capable of producing objects like these throughout the galaxy. Oumuamua, discovered in 2017, was notable primarily for its unusual elongated shape and its lack of an obviously active gas-venting coma, sparking years of scientific debate about its precise nature that, even now, remains only partially resolved. Borisov, discovered in 2019, behaved far more like a familiar, ordinary comet from our own solar system, with a chemical composition that, while clearly originating from another star system, still fell broadly within the range of what scientists would expect from typical cometary material. 3II Atlas, the largest and most extensively studied of the three, has now revealed something neither of its predecessors could: direct, detailed isotopic evidence pointing toward an origin billions of years older than our own solar system, formed under conditions colder and more extreme than anything typically associated with planetary system formation, as scientists currently understand it. Taken together, these three brief, unrepeatable glimpses into material from beyond our own solar system are steadily building something astronomers had, until relatively recently, only been able to theorize about in the abstract: a genuine, if still extremely limited, comparative sample of the kinds of chemical environments capable of producing icy bodies across different regions and different eras of our galaxy's long history. NASA's own description of the discovery captured this comparative value directly, describing the opportunity to study an interstellar comet as being similar to studying an artifact recovered from an ancient culture, one that offers direct insight into that distant time and place, while also allowing for meaningful comparison against our own. Webb's observations of 3I Atlas's composition are, in that same framing, actively demonstrating just how unusual, or perhaps how comparatively fortunate, our own solar system's formation history may genuinely be, relative to at least this one small ancient sample of material formed somewhere else entirely, under conditions our own solar system apparently never experienced. The timing of this entire observation, worth emphasizing one more time, was genuinely narrow and irreplaceable. 3I Atlas's coma was only bright and active enough to provide this level of detailed chemical measurement for a limited window following its closest approach to the sun, as residual solar heating continued driving gas off its ancient, long-frozen surface. As the comet has continued moving farther from the sun throughout the first half of 2026, that activity has been steadily fading, and the object itself is now well on its way back out of the solar system entirely, following the same hyperbolic trajectory that brought it briefly close enough for observation in the first place. There will be no return visit. Once 3I Atlas crosses back out past the orbit of Jupiter and continues onward into interstellar space, it will do so permanently, carrying with it whatever additional secrets about its ancient 10 to 12 billion-year-old origin remain still unmeasured, unread, and now permanently out of reach for the remainder of human history, or at least for as long as it takes another comparably favorable interstellar visitor to happen to pass close enough to a sufficiently powerful telescope to be studied in this kind of depth again. That's really the quiet, underlying urgency behind a discovery like this one, the part that's easy to lose sight of amid the more striking individual numbers, the deuterium ratios, the carbon isotopes, the staggering 12 billion year age estimate. Every one of those measurements came from a single, narrow, unrepeatable window of opportunity, gathered by a team of astronomers who understood exactly how limited their chance to study this particular object actually was, and who used the most sensitive infrared instrument ever built by humanity to extract as much genuine scientific value from that window as the physics of the situation would allow. What they found wasn't a mystery in any conspiratorial sense, and it wasn't hyperbole to describe it as surprising, since NASA's own scientists used that exact word themselves in their own published summary of the findings. It was something quieter and, in its own way, considerably more profound. Real, hard, physically measured evidence that somewhere out among the billions of stars scattered across our galaxy, long before our own sun ever formed, long before Earth existed in any form at all, ice was accumulating in an extraordinarily cold, ancient corner of the universe. Chemistry that has now, after drifting silently through interstellar space for potentially 12 billion years, finally been read, however briefly, by instruments built by a species that didn't yet exist for the overwhelming majority of that ice's extraordinarily long history. 3I Atlas is still out there right now, moving steadily back toward the interstellar darkness it emerged from roughly a year ago, carrying whatever remains of its ancient chemical story with it, permanently beyond the reach of any telescope on Earth, once it finally slips back past the edge of what our instruments can meaningfully observe. What Webb managed to read from it during that one narrow window in December of 2025 will likely remain one of the most detailed chemical portraits of a truly ancient interstellar object that scientists have, or will have, for a very long time to come. If you want to keep following what researchers continue to learn from that data as further analysis of Webb's observations continues throughout the rest of this year, that's a story still actively being written. Subscribe if you'd like to follow where it goes next.